Our next speaker is Dr. Hans Stein, professor at the University of Illinois, and his presentation, Why a New Net Energy Value of Soybean Meal Fed to Pigs is Needed.
Thank you, Dean. Thank you. What I'll talk about today is a little bit about net energy. First of all, to those of you who watched my presentation yesterday on nitrogen retention, I do have to apologize. There's a little bit of overlap because I will talk about some of the same things. But the take-home messages I hope you'll get from this is, first of all, that if we feed low-protein diets, we do not necessarily get more net energy into the diets, and that has something to do with the net energy of soybean meal. We'll talk a little bit about that, why that is, but just remember that low-protein diets do not necessarily give us more net energy. Secondly, the modern genotypes of pigs, they have greater nitrogen retention. I talked about that yesterday, and I'll show you a few examples of why that is important for net energy. We'll talk a little bit about that. The third thing I hope you'll remember, here we come. The third thing I hope you'll remember is that we do need a new system to calculate net energy so we can take into account the pigs we have today and the net energy of the protein, which has changed over the years. We'll talk a little bit about that also. And finally, the net energy in soybean meal is likely between 90 and 100% of corn. That's our best estimate we have today. And that is quite a bit greater than what you will find in the book values. So let's try and get started here and see. If we go back to the 1980s, there were some estimates published on what are the net energy value of different nutrients. And you'll see the nutrient with the most net energy is fat. 90% has been presented as a number for fat, and that is what we expect we'll get. And I'll show you some numbers on that for sure. Fat has a high net energy value. If we look at starch, 82%, so pretty high also. That's also a number that was published there, and that is probably consistent with what we see today. But then we get to protein, and you'll see it's only 60%. 60% efficiency of the energy in protein when it's deposited into a pig. And so that's the one we will talk a little bit more about because it's a pretty low value here, you'll see. And then fiber has the lowest value. Sometimes you could say it's 0 because if it's lignin, which is part of the fiber fraction, it would be 0. Some of the soluble fibers will probably have a pretty high efficiency, so that could get up to 60%. But these are the values that have been used to generate the net energy systems that we have. So some of you know we do have an indirect calorimetry unit at the University of Illinois that we constructed about almost 10 years ago now. And in our system, we have group house pigs. So we have 4 pigs typically per chamber. And it's completely closed, so we can measure the gas exchanges, oxygen consumption, and carbon dioxide and methane production. And we can collect all the feces and urine as well. So that's where we are doing our net energy work. So just to show you a few examples, I said before that fat has a very high net energy value, and here you'll see an experiment where we had 0% soybean oil, 1.5, 3, 4.5, 6, or 7.5% soybean oil, and that's added into a corn soybean meal diet. And what happens when we add fat? Well, as you would expect, and as that high number I showed you before would indicate, we increase net energy linearly as we add more fat to the diet. No surprise there. Same thing with fiber, had a very low net energy value. So here's an experiment where we again used the corn soybean meal diet to start with as a control, and then we added 6% soybean hulls, 12, 18, 24, or 30% soybean hulls. And you'll see in this case, we get a linear reduction in net energy. And again, this is consistent what we would expect based on those numbers for efficiency I showed you before, that fiber has a low net energy value. So far, so good. But then we come to protein. And in fact, one of the very first experiments we conducted in our calorimeter facility was I wanted to have an easy experiment where I knew what the outcome was, and I thought I knew that a low-protein diet had more net energy than a high-protein diet. So we just formulated two diets, 14% or 21% crude protein, and you'll see what happened to net energy here. There was no difference. And you remember, the efficiency of crude protein was supposed to be very low, similar to some of the fiber components. So we should have had a much lower value here for the 21% diet compared with the 14% diet, but we didn't. There was absolutely no difference. So that was a little bit surprising. So we had to think more about what is causing this and what we can do. And so we can think about these net energy equations that we have. And here's the CVB equation. And CVB, that's the only feed composition table you'll find where everything always adds up to 100%. And the reason for that is that they calculate a rest fraction for the fiber. They don't analyze all the components, they calculate what they call rest fraction. So when they calculate net energy, they will they will calculate from each nutrient crude protein, here digestible crude protein, and this is total tract digestible crude protein, ether extract, again digestible ether extract, the starch, that's total starch not digestible, they have a value for sugar, and then you can see the rest fraction here, which would be everything else that they cannot analyze. So that's why it adds up to 100%. So that's how they do their net energy value. But what I want to point out here, other than the rest fraction here, you look at this value for crude protein, that value is quite a bit lower than it is for starch, right? It's lower than fat, of course, but it's also lower than starch. And that goes back to those efficiencies I showed you before. Remember where we had 82% for starch and only 60% for protein. So that kind of reflects those lower efficiencies for crude protein. So that's ingrained in this CVB system here. The system we used for in NRC was a Noblet system. And that's a system where we start with the digestible energy. Some people would argue it's not really a net energy system, it's just an adjusted DE system, and I don't really care what you call it. In one way, by starting with digestible energy, Noblet, he takes care of a lot of uncertainties that we have, because that's a value we can definitely get with a relatively high precision. And so I think it's kind of a brilliant way of doing it, starting with digestible energy and then adjusting from there. And you'll see he adjusts, he'll say if there's a lot of fat in your diet, ether extract, you add a factor. If there's starch, you add another factor. So again, those two nutrients with high energy efficiencies, you add a little bit, but then you get to the crude protein here, you really subtract, you really hammer down the net energy if there's high crude protein, because the assumption is that that protein has a low efficiency. And so you really get a low value here. And then the fiber will subtract something also here. And I'm always amazed that the negative value in front of crude protein is even higher than in front of ADF. Think about ADF is lignin and cellulose, right? Which is not very, very high in net energy, but still the adjustment for crude protein is greater. So that's the system we have today. Now, what does that mean? That means that corn will have a greater net energy value than soybean meal. So we go to NRC, this is on a dry matter basis. You have a little over 3,000 kcals in corn and only 2,300 in soybean meal, which is about 78%. So that's because we have this low net energy estimation for crude protein. If you look into different feed tables, here we have the NRC, we have the INRA table from France, and we have the Brazilian table here. You look at digestible energy, very close to each other. Metabolizable energy, very close to each other. And because of that, when you calculate net energy based on that previous equation, you get a value here. Those values are very close to each other. Pretty good agreement, right? But we have conducted DE and ME experiments for many, many sorts of soybean meal, at the University of Illinois, and we started noticing that we would always get DE values that were greater than these values here. And I don't know if it's because the soybean meal has changed or it's because these are all wrong, I don't know, but we consistently got greater values, and we have greater ME values, and therefore, of course, when we calculate the NE, we also had a greater value here. So if you start out calculating net energy from DE, then you would rely on having the correct value for DE. And we started questioning that if these DE values are correct. So that was the first thing that we noticed, and that's the first reason that in the title I said why we need a new net energy value for soybean meal, simply because the DE value is incorrect. We are pretty convinced about that. So that was DE. Now then, we saw another experiment or another data set from China, published in 2017 for net energy. This is measured in calorimetry, and you'll see a value that's about 400 kcal greater than what NRC would estimate here, 2710. This is from indirect calorimetry. So that is more than you can explain just from our adjusted DE value. This is a greater increase. So we looked more into that and said, what happens when if you look at that, think about that corn value I showed you before, and the soybean meal values, corn greater than soybean meal. So if you formulate diets with different amounts of crude protein, that means if you take crude protein down, we will take corn up, soybean meal down, and add synthetic amino acids, right? So if we do that, theoretically, we should see this linear increase in net energy simply because corn contains more net energy than soybean meal. So it should go up like this. And I had already showed you that in that first experiment, we didn't see a difference. So we were kind of eager to repeat this. And here is what we expected to see based on NRC values. And we then fed these 6 diets to our pigs in the calorimetry unit. And this is what we got. Absolutely no difference. Absolutely no difference. So again, exactly like in the first experiment where we just compared 14 and 21%, we are not able to demonstrate a reduction in net energy when we reduce crude proteins in the diets. Okay, so that again told us maybe that estimation of net energy in the protein fraction, maybe we have somehow underestimated that, because it doesn't look like soybean meal has less net energy than corn here. It looks like it's pretty much the same. It doesn't matter if you take soybean meal up and corn down and whatever, we get the same net energy. So that was interesting. So we thought, okay, let's try and do it one more time. So we conducted another experiment where we had 4 diets, one with 20% crude protein and 35% soybean meal. So this is for younger pigs. Another diet with only 16% crude protein and 24% soybean meal. And then we have more corn here. And then we go to a little bit less soybean meal and less soybean meal, down to 19%. These are formulated for pigs from 25 to 50 kilograms based on NRC. Pigs were a little bit greater when we started, but these are the diets we had. What happened to average daily gain? We fed them for 4 weeks. What happened to average daily gain? Absolutely nothing, indicating that we have met all the requirements. Gain to feed, same thing. No change among these 4 diets. So again, indicating that we have formulated the diets correctly, we have met all the requirements. But what about net energy? Yeah, again, it definitely did not increase when we reduced crude protein. One more time, no increase, and in fact, in this case, there was kind of a linear trend for a reduction in net energy in these diets as we reduce crude protein. So 3 times we have conducted experiments in different ways, where every time we have concluded that it's not correct that the low protein diets, they give us more net energy, as would be suggested from the equation we use in NRC and for the corn and soybean meal net energy values you have in NRC. So now you understand why the first take-home message was low protein diets does not give you more net energy, because I think we are pretty sure about that. Okay, so let's go back to this equation here and look at what is happening. And think of this 0.91 here in front of crude protein. What does that mean? Where did that number come from? Well, it came from nitrogen balance studies, and Noblet, he's published a paper later where he said it can be assumed that nitrogen retention will never be greater than 45 to 50% of absorbed nitrogen. And if absorption is maybe of digestibility is 90%, then you could translate that to be about between 40 and 45% of energy of digested nitrogen intake. So if you look at that, those of you who saw my presentation yesterday would see that we have seen that over the years we have increased nitrogen retention pretty significantly, right? And in fact, if you do it on a regression basis, you can calculate the increase. It's the 32% was what we have in 1964, and then we have since that time increased by about 0.52 percentage units every year after that. So that means that in 2024, 60 years later, we would have had 63% nitrogen retention. So you can see that's where we are here, right? And that's pretty consistent. And if you look at where Noblet, he did his work in the 1980s, here, you go out here, it's exactly 45%. So it's not that he was wrong. He was exactly right. Pigs, they had at that time 45% nitrogen retention, but the pigs have changed since that time. And that's why the net energy of the protein fraction has changed, because now they retain more, right? They retain more nitrogen. That's our conclusion on this. So here are 5 recent experiments from our group where we have measured nitrogen retention. See, all of these, we are right there around that 63, 64% that I showed you before based on the regression line. So certainly we are above the 40 to 45%. So what does that mean for net energy? Well, if we try to do a quick calculation, say, what does a difference between 45% retention and 70% retention of nitrogen, what does that mean in terms of net energy? So here we make some assumptions. The one is that if a pig is deaminating amino acids to synthesize net energy from the amino acids, which they would do for, if you only have 45% retention, then 55% of all the protein would be degraded, so the pig would deaminate those amino acids and retain the energy that could come from there. The net retention there, we assume, is 58%. In contrast, if the pig is using these amino acids for protein synthesis, we assume it's 83%. So if you take a 46% soybean meal and go from 45 to 70% retention, you add 163 kcal of net energy to that soybean meal, right? So this increase in nitrogen retention has a direct impact on the net energy of soybean meal, or more correctly, a direct impact on the net energy of the protein in diets. This would not be only for soybean meal. This would be assumed to be the case for all protein sources that would have this relationship. So if we add it up here, remember I said we have more DE in soybean meal. Will give us about 170 kcal extra net energy based on an average of what we have seen in our team. Then we have the 165 kcal I just showed you for the increased nitrogen retention. That means we have 335 kcal net energy more in soybean meal than you would get from NRC today. Okay? So what is, we can calculate a new net energy value in soybean meal. If we take the 2087, that's an as-is basis from NRC, add these 335 we have here, now we get 2422 or 2691 on a dry matter basis. So that would be our estimate for a new net energy of soybean meal value here. Does that make sense? Well, what did we say here? 2691 kcal per kilogram dry matter. And look at what they found there in China, 2710. So very, very close, right? So that doesn't prove it's correct, but it kind of gives us an indication. Some other estimates have been, I took here from corn soybean meal diets where they published net energy value of the entire diet, and then I subtracted out what we assume is the net energy of corn, and then we could calculate from there what do we have in the soybean meal. And it's not the same everywhere, but you'll see we are up here near the 2700 in some of these experiments. And for sure, in all of them, we have estimated more net energy in soybean meal than what NRC would suggest we have today. So all of these point to the same direction, that we have more net energy in soybean meal, and that is why the title said why we should have a new net energy value for soybean meal. So a few conclusions here before we stop. Net energy of soybean meal is greater than NRC. I hope you have. I've convinced you of that. We need to use a greater value. And one of the reasons we need that new value is that the modern pigs we have today have greater nitrogen retention. Our current prediction equations, we don't believe that they necessarily are completely accurate. It goes by itself here. So that's a need. There's a need for updating these prediction equations for net energy. And we have seen no evidence that low-protein diets have greater net energy than diets with higher protein. And when we say higher protein, these are basically diets where we start with just corn and soybean meal, no synthetic amino acids. It is possible, and I'm not an expert on this, but it's possible some of those responses are due to some of the biological components in soybean meal. Others have talked about that. If that is the case, then we would assume that if we have some of these biological components, we would assume some of these effects are specific to soybean meal. We don't know that for sure, but otherwise we would assume it would be maybe general to protein across all ingredients. And we think that the net energy of soybean meal today likely is between 90 and 100% of the net energy of corn, and that aligns very well with what Dr. Gaines presented earlier this afternoon. He said 97%, I guess. So with that, I want to acknowledge the team we have. This is our current team of graduate students and technicians, etc., postdocs, and we have a website here. You can go on our website if you have an interest in learning more about what we are doing. So with that, thank you very much.
Thank you, Hans.